Okay, so we're about to get to the point where we're going to start running reciprocating engines. Now that we understand how they all work, we need to be able to run them, troubleshoot them, and then fix whatever thing may be wrong with them. So in order to do that, we need to understand some of the data that we're going to get in the cockpit of that engine that will kind of give us a indicator of what the engine's health may be. First off is fuel flow. So let's talk about what fuel flow is, why is it important, and how can we, as mechanics sitting there in the cockpit, read the fuel flow to make a decision on if that's good or bad. All right, so on reciprocating engines, a lot of times you won't see fuel flow, you'll see fuel pressure, and that basically serves the same purpose. It will turn around and tell you, hey, look, this is the fuel pressure in the line. You can infer then that the fuel is flowing, and you don't get quite the same amount of, I guess, fidelity as you would with the gallons per hour fuel flow meter, but it does let you know that, hey, look, the fuel pressure is there, so therefore we can kind of know that the fuel is moving through the line, so we get to the same point as that we would with a gallons per hour meter. However, we just don't know as well. But all it's really doing is telling you that, hey, look, the fuel is in the tank. It's being pressurized and then sent up into the carburetor and then onwards to the cylinder. So you can be relatively assured that the engine is getting power. All right, now this little cluster right here kind of gives you an idea of what you could potentially see on different aircraft. Now the fuel quantity on the right-hand side, there's all different types of fuel quantity gauges out there, so, and we have a whole class on fuel systems, so I won't belabor the point on that one. But on the fuel flow and the fuel pressure, it really kind of shows you what the possibilities are in a small reciprocating engine. Most all of them, like I said, they have fuel pressure. That's what my aircraft has is going to be a fuel pressure. It's just a little gauge that has like an arm that sticks up into the green there, to let you know that, hey, look, the fuel pressure is positive and it's running at about so many psi, and you can infer that's about right. The gallons per hour, that's just telling you how many gallons the engine is using per every operational hour, and that will also help you with your flight planning, because you'll be able to sit back and say, like, well, I know I have 100 gallons left and we're burning 10 gallons an hour, so therefore I can fly for another 10 hours, and if I'm going 100 miles an hour, then I know I can fly 1,000 miles based on these fuel settings, provided nothing changes, and then you can make adjustments accordingly. Now, since this is all in the context of doing a engine run, we can say, like, hey, look, if the fuel pressure is not there or the fuel flow isn't there, then obviously the engine's not going to run correctly, because it's not getting enough gas. It's either not getting any gas at all, so it's not going to run at all, or it's getting just enough, and it'll kind of like just stutter along and kind of bounce around, and it won't actually run smoothly. Now, there is a chance that it overpressurizes it, and you can overrich the mixture that way, or simply just flood the engine totally, and it won't fire either, because there's not enough air to actually ignite the amount of fuel that's in there. And even if it did, I don't know that you would want to, because in that scenario, the engine may very well explode, because there's so much in there, if it ever got going anyways. So either way, this is just kind of one of those engine health metrics that doesn't necessarily tell you everything, but it absolutely is the canary in the coal mine, and kind of points you in the direction that you want to go to know how to go about fixing it. Next one is temperature. Now, temperature is a very wide-ranging thing, and we're going to get temperatures across the spectrum, from cylinder head temperatures, exhaust gas temperature, all the temperatures that you could potentially. Okay, so the first one that we're going to talk about is just carb air temperature. Now, this is really important, because if the carb gets too hot, then it could potentially start causing the gas to turn to vapor before it actually gets to the point where we want to atomize it, and that could lead to vapor lock. But more importantly and more likely is that the carb air temperature is too cold. Now, as it gets too cold, two things are going to happen. One is that the cold temperatures on the side are going to cause that fuel to condensate on the sidewalls of the Venturi and not be turned into it would prevent it from becoming a form that would allow it to combust. Then probably the bigger one, however, is going to be carb ice. If it gets too cold, then water vapor in the air will condensate and freeze, and then eventually just clog the engine up. And so if you have a very cold carburetor, one of the things to look out for is carb ice. Now, typically there's a carb heat in there that just redirects exhaust gases over the top of the carburetor and causes it to warm up and then therefore melt that. So it's pretty easy to fix. And it's also fairly easy to detect if you just simply know what you're looking for. Carb ice is pretty telling. You're going to be in a cold, damp environment, and the engine's going to start running rough, almost like it doesn't have enough fuel, and it's going to kind of come out of nowhere. And so but if you have a carb temperature or air temperature gauge on there, it will help take a lot of the guesswork out. You can just look at it and you know that, oh, look, it's super cold, engine's running rough, it's probably carb ice. Let's put some carb heat on there and see if we can get that ice to melt. Okay, the next temperature gauge we're going to look at is going to be oil temperature. So oil, obviously, if it's too cold, it's going to want to be super duper viscous, and it's not going to have the same cooling or cleaning effects that we want it to have inside of the engine. So obviously that's bad. It won't necessarily lead to the engine running rough per se. However, there are examples of of people operating in the Arctic where the oil basically has water in it and then it just freezes solid and it won't run at all. So that could be a problem. The more common oil temperature shenanigan that you're going to run into is that the oil is too hot. Now, two things will lead to the oil running too hot. One, and probably the worst case scenario, is that there's not enough oil in the system. If there's not enough oil in the system, then the same oil is getting cycled through faster and faster and faster, causing the temperature to rise because it doesn't have a chance to bleed off any of that extra heat because there's just simply not enough of it. Whereas if you have a sufficient amount of oil in the system, and that oil will go into the sump. It will start to cool off, and before it gets reintroduced back into to the engine again, cycle through to pick up more heat, more trash, and all that good stuff. Now, so one of the ways to know that, hey, look, you don't have enough oil is simply by watching your oil temp. If it starts getting really, really hot, you're likely going to be running short on oil. The other scenario where you get really warm oil is that if the oil starts to break down over time, if it's been a long time between oil changes, what happens with oil is that as it gets heated up and cooled and heated up and cooled, it's effectively being refined even more than it would be inside of a refinery. And so you're getting that oil to start to break down and become thinner and thinner and thinner and thinner. And as it becomes thinner, it can't hold as much heat. And so as it starts to not being able to hold as much heat, the aggregate temperature of the oil itself starts to come up because it's not able to grab that heat and then disperse it as it goes. So it just starts running hotter and hotter and hotter and hotter and hotter as that oil temperature goes through the engine and returns back to the sump. It's just like super duper hot because it's not able to grab that heat and then bleed it off into the system. So therefore, you'll start to see the engine run hotter and hotter and hotter and hotter because the oil is being less and less effective, leading the oil temperature to actually go up. And so there is definitely a cause to say, hey, look, you got super high oil temps. First thing to do is check the oil. If the oil is good, then we're going to change the oil, and then if it runs again, then we might have another problem of some other variety. But those are kind of like your base troubleshooting steps. But the main thing to take away is that oil temperature is one of those engine health metrics that you really want to pay a lot of attention to, be it reciprocating, turbine, or whatever, because it really kind of is the canary in the coal mine a lot of times. Okay, the next temperature we want to pay attention to is EGT, or exhaust gas temperature. Now, this gauge right here is for a twin-engine airplane, and is incremented in the hundreds. That 8 at the bottom is representative of 800 all the way up to 1600 degrees Fahrenheit. Now, EGT is it plays a lot more, a bigger role in turbine aircraft. That's really kind of the, I guess, indicator that, hey, look, the engine's running or it's not running. However, that being said, it has become a kind of a staple with a lot of reciprocating engine health metrics, especially as more and more digital displays start to get worked into the mix. It's very easy to detect EGT. It's simply just a probe into the exhaust. As the exhaust goes by, he'll tell you what, hey, this is what the the EGT is at here. Now that tells us a lot of things. It tells us basically what is the interior health of that cylinder look like. If it's super duper hot, then there's probably a reason it's really really hot. It's the mixture's not set right. The valve isn't working correctly. It's the metal is getting too thin or whatever the thing is. But the point being is that it really kind of points us, hey, look, there's something not right here. If it's super super low, then we know we have insufficient combustion of some variety or for some reason. So EGT becomes this metric that we pay a lot of attention to, especially in the turbine world, but even in the recip world. If we notice that hey, look, the EGT is way off, and especially if we have like a 4-cylinder engine and one of those EGTs is just super high or super low, then we can pretty well bet there's something that's not happening correctly inside of that cylinder, and we need to investigate further. Okay, the next one we want to talk about, and the last one we want to talk about in terms of temperature, is going to be the cylinder head temperature. Now this is something that's unique to just recip engines. So we want to know what is the temperature of the head of the cylinder, so the very top of the cylinder. What's it running at? Is it running in 200, 300, 400 degrees Celsius? What this gauge is actually set in. And what does that tell us? Well, it by itself, it can only really tell us something if it's really, really high or it's really, really low. But whenever you look at all the different cylinders, now you can start to see, hey, look, this cylinder is cool compared to this cylinder. Why? And like you start to kind of like try to figure out, like, hey, look, is it missing every so many cycles? It's not firing correctly, so it's not generating as much heat. Are all the other cylinders just going bad, and this is the only good one there, which is also a possibility. I'll give you a real life example on how CHT factored in. Is I had a problem with my aircraft engine, and we thought it was the magneto wasn't being timed, and then whenever we ran it up after having spent a long time timing magnetos, we went from one cylinder to the other just with the back of our hand, and like 3 of them were you couldn't barely touch it. I mean, it almost take the hide off of you, just barely kind of just checking it. But one of them was cool, like almost like it had been in a microwave or something, where it was still warm, but it wasn't like super duper hot. And so that let us know that, hey, look, this cylinder right here, this number 1 cylinder here, is not right. And when we started looking at it, one of the ignition wires had failed on us, and that was the problem. Now, had we had a cylinder head temperature gauge on the dash of the plane and had been watching it, we would have bypassed a lot and just said, hey, look, the number 1 cylinder right here has failed on us, and we're not really sure why. And come to find out, it was just a wire. It was a really simple fix, and then the plane was back in the air. But CHT would have been very, very helpful in that particular instance. Next is pressure. We're going to look at all the different pressures that we're sitting in a reciprocating engine powered aircraft. What does what pressures are we looking for, and then how do we tell one way or the other? Okay, so one of the biggest pressure gauges we've already covered, and that's just simply fuel pressure. Fuel pressure or fuel flow, same. I don't want to belabor the point on that, but fuel pressure is going to be important, especially on older recip engines. That's how they're going to get indicated. All right, manifold pressure. Now, this is a real important one. So whenever it says manifold pressure, the manifold it's referring to is the intake manifold, okay? Now, the manifold pressure is going to help you obtain the correct power setting for the engine. It's going to say, hey, look, we know that for this mode of flight, for this maneuver, we've done the math, and we know that, hey, 30 inches of manifold pressure is what we need to see in order for the engine to produce sufficient power to do this thing, whatever the thing is. Takeoff, landing, you're going to do a barrel roll, whatever. So you're going to set the prop lever to where you get the right manifold pressure that's there. That means that, hey, look, the engine is turning at a certain RPM, and you want to load and deload the engine so that way it speeds or slows it up, so that way you get the right level of pressure inside of that intake manifold, so that way you can continue to make the same level of power that you want to make. Now, this particular gauge is corrected for temperature and altitude internally, so you don't have to worry about any of that. It's simply you just simply set the manifold pressure, and off you go. Now, obviously, if you have the prop set way far forward, it's super aggressive, and you pull the power back, you're going to drop the manifold pressure. So there is an interplay between the two. However, this allows you to have like another metric to know how that engine is set, or what's being demanded on the engine. But yeah, so that is manifold pressure. Okay, oil pressure is another big one. Oil temperature, it will tell you kind of the health of the oil. Oil pressure, a lot of times, will tell you how much oil is actually there. If you have a lot of oil in there, the pressure generally goes up. If you have a low amount of oil in there, the pressure generally goes down. So if you start to see, a lot of times you can see this interplay. As the oil pressure falls off, oil temperature comes back up, generally speaking. If you ever watch like an engine fail in flight, you'll see the oil pressure will start to decline, and the oil temperature will start to come up. As that oil starts to exit the engine, what ends up happening is that the pressure drops, because there's simply just not enough there. I mean, you think about, like, if you had a Coke, right, and then you put it out there on a hot day, and it's full, and it hasn't been opened yet, and you just sit there and just hold that bottle, and you can barely squish it in with your hands. But if you pour half of it out, you can grab and squeeze it, and it's not a big deal at all. Well, same thing with oil in an engine. If there's too much oil in there, if there's a lot of oil in there, the pressure is super high. But as it starts to fall off, the oil pressure goes with it. And then, as we discussed earlier, as there's less oil in there, there's more heat can be concentrated per unit of oil. So therefore, the oil is going to come up in oil temperature. So those two are almost like inversely related. If you rarely ever see both of them go one way or the other together, they're usually going opposite of one another. And so there's an optimal amount of oil pressure, just like there's an optimal oil temperature, and that's where you want to keep it. And if you have too much oil, too little oil, one way or the other, or too old oil, or whatever, it'll indicate that on the dial as well. And you need to make whatever changes happen to make it work. What about annunciators? Annunciators are going to give us an indication that there's something going on in the aircraft. What could we be looking for, and then what potential annunciators could we see in a reciprocating engine? Okay, while not really an annunciator, the tachometer doesn't really fit anywhere else, but it's probably one of the most important engine health monitor apparatuses that's in the cockpit. What all the RPM gauge is effectively going to tell us is how many revolutions per minute in hundreds, at least on this gauge, the engine is operating at. So if it's sitting at the 5 there at the bottom of the green arc, it's only making 500 RPMs. Now, why is that important? Well, if the engine is set at a certain power setting, so you put it at 1,000 RPMs, then you can infer certain performance characteristics. You can infer certain fuel burn, all this other good stuff. At 2,000 RPMs, that's where you're going to do your magneto checks. And so, like, whenever we go to check the magneto and it drops down, so many RPMs with such a differential. So, like, usually it's like 175 and then 50 between. That is going to be done at about 2,000 or so. Now, depending on the engine, so like my engine is a IO320 Echo 2 Alpha, the bare minimum power it can make at full throttle is 2,300 and some change. I think it's 2,375. I can't remember. But it's not supposed to make greater than 2,575. So as long as you're at max power, you're in between those two tick marks, then you're good to go. all right, then you should be fine. Okay. Now, why the range? Well, the range will depend based on the quality of air that's coming into it. It's not turbocharged or anything else like that, and so basically, it's just got a downdraft carburetor that's just sucking in the outside air and then into the engine, and then the engine just produces whatever power it produces. And so, like, if you have a really hot, humid day that's just not really good for performance, it might be closer to that 2300 mark. But if you're in a really nice, cool, crisp day that is super cold, then and dry, then it might be closer to the 2575 mark. But so that there is a little bit of range there. Now, this is usually the first gauge that's going to tell the pilot, hey, look, there's something wrong with the engine. I just can't get the power, or I'm over revving, or whatever the problem is. You know that, hey, look, there's some sort of issue at hand, and we need to investigate further. Then we'll go to like our oil temperature and all this. And then this all happens almost instantaneously. You're gonna like, well, I don't have the power that I need, and you look over and off you go. This is also a good way to set the performance for the airplane in the traffic pattern. So like whenever you make certain turns in the traffic pattern, you might set it to 2,000 RPMs or 2,300 RPMs or 1,700 RPMs, or you might pull it to idle or whatever, depending on what you're trying to accomplish and where you're at. And so this is oftentimes the gauge that the pilot's going to be looking at the most in order to set the RPMs correctly. Now, you as a maintainer are going to follow suit, and you're going to sit there and say like, hey, look, at max power, so I'm going to go full throttle. Well, how many RPMs do we have going? And if it's in the range, it's like, cool. Then you go and say like, okay, how's our oil pressure look? How's our fuel flow look? How's all these other downtrace things? If it's not right, then those downtrace gauges are going to tell you, hey, look, it's not right because we don't have the fuel pressure, or hey, look, it's not right because the oil is acting up, or whatever. And so this is like going to be kind of like, it's the first block on the flow diagram of troubleshooting as you go. It's just like, what's our RPMs at, and why isn't it not correct? But yeah, so that's your RPM gauge. Okay, so let's talk about actual annunciators now. Now, not every aircraft has annunciators like this. A lot of them do. They're usually right there at the very top of the panel. Like, so you can see this example. It's sitting on top of the altimeter and your turn slip indicator, your artificial horizon, and it's going to sit there and just like it's just a little box of lights, little LEDs that will light up and tell you, hey, look, something is going wrong somewhere else that requires your investigation. And the idea is that like somewhere on the panel, you could lose, like, say, oil pressure or whatever. And in theory, it's just a gauge, and it's just moving, and you missed it because you're too busy talking or whatever the thing is. They wanted to have something in there that could actually get your attention, and it would light up and say like, hey, look, you need to go investigate. So on this in particular one, we have three annunciations, if you want to call it that, three lights that are illuminated. One is oil pressure. So like if the oil pressure gets below a certain point, or even above a certain point, it'll light up and say, hey, look, oil pressure, and then that tells you, hey, look, you need to do something to make that oil pressure go away, or not go away, but like oil pressure right. It's not correct right now. You want more oil pressure if that light is lit up. The other one is left and right vacuum. So this in particular aircraft is going to have a vacuum pump that's going to be hooked up to both the altimeter and that artificial horizon, and it's going to be sucking vacuum to spin those gyros to allow you to navigate and operate like you normally would. Well, it's saying, hey, look, there was a vacuum failure on both the left and the right pump. So, assuming this is a twin-engine aircraft, or maybe it does have twin vacuum pumps for redundancy, who knows? And it's letting you know that both of those pumps have failed. And then, lastly, on the right-hand side, you have volts. It means that, hey, look, it's whatever it has on the engines, alternator, generator, whatever. It's not producing enough power, and so like you have a low voltage alarm saying like, hey, look, there's something that's not right, and so you need to go and check it out. Now, this is probably what's ended up happening on this one. It's either it's not on test mode because you can see the tester right onto the right. So usually you can flip it up and all those lights will come on. Make sure that none of the lamps are burnt out. It's probably like the power's turned on to the engine, but the engine's not running yet, and so it's giving you all those indications because basically the engine's not turning. If the engine's not turning, you're gonna have oil pressure, vacuum, or voltage. So that's probably what's happening here. Okay, so here's a little bit more complicated aircraft. You can see there's a lot more happening on this particular annunciator panel. You have low fuel, low generator, or left fuel off, left generator off, left fuel shut off, left all the L's all the way, for NTS check. Beta means that, hey, look, the propeller is turned all the way back around into its beta range. You have fuel transfer, engine anti-ice, windshield air, heat, air duct heat, low hydraulic fuel, low oil pressure, and then even the door is not locked. Hydraulic pressure, on. All these things are just cautions and warnings in there. Now, granted, green is just simply like say like, hey, look, this thing is on. So you can see the left engine anti-ice is just saying, hey, look, it's on. The cautions are saying like, hey, hydraulic pressure's on. You might want to pay attention. Pay attention to that. You have fuel level low. These are just cautions. And that means that the plane's about to crash. But hey, look, this is something you need to pay attention to. However, red means, hey, look, this is something you really need to like hone in on. Like the door is not locked. All right, so that means that the door could fly open and you could lose a passenger that way, or cause the plane to yaw, or whatever the thing may be. You have low oil pressure. It's never good for anybody if the oil pressure is low. Now let's talk about EICAS, the Engine Indicating and Crew Alert Systems. What does that look like on a reciprocating engine, and what are we looking for on it? Okay, so let's talk about EICAS. EICAS stands for the Engine Indicating and Crew Alert System. So basically, EICAS is kind of like the next generation engine gauge. So instead of having all of these different gauges and running all these mechanical things, we have a series of data buses and usually 1 to 2 computers that process that information, condition the signals so that way they're usable, and then it gets fed up to the pilot. Now, this in particular is a really popular Garmin one, so I chose it to put on here, that you'll see in some older airplanes, and they've taken like the size of, like, say, an altimeter and kind of the shape of it, and built a display that gives you all the information that you need. So just kind of like, let's just read this together so that way we kind of understand what it is we're looking at. So at the top, we see that the engine is set to 75% power. So that means that the RPM is sitting like right there at the 75% mark, and you've got about 25% more that you could potentially go and get some more RPMs out of it, but you're not going to get that much more of it. And the likelihood is that's probably going to be about the most efficient place for the engine to go. So typically you're going to cruise at about 75% to make everything work. You have your manifold pressure on the left right below it with the RPMs right there. So that tells you that's all your engine power kind of. It's not a quadrant, but that section that above that white line is all about engine power. Now the section to the bottom left is all about engine health, right? So CHT, EGT, TITs, that's a turbine internal temperature, is all like happening right there. Now, and then you have the different CHTs and EGTs per cylinder right there. So if you had one that was like way off or way out there, then you would know there was something wrong at there. Now it seems like now I could be wrong on this, but the H is illuminated with a line under 3, which means that it's probably hotter than the rest for whatever reason. You notice that the CHT is also, they're all in blue because they're right above that red line, except for the one on the far left hand side, which is actually not, because it's still green. All right, on the right-hand side is more your classic engine data that you're looking for. You have your oil pressure, oil temperature, fuel pressure, and your fuel flow. So this one actually gives you both. You have like your fuel pressure is at 15.9 psi, but your gallons per hour is 15.5. And so that kind of gives you like your flight planning data, lets you know, hey, look, based on how much fuel we have available, which is going to be right below us, we should be able to know that, hey, look, gallons per hour, we have so many hours of flight time. If we're making, so many so many knots true, we should be able to get to place A or B or whatever the thing is. Now on the bottom, it'll tell you, hey, look, you're doing 10 amps off your battery. You've got 26 gallons of fuel in one wing, 31 gallons of fuel in the other wing, and your batteries hold steady at 28.1 volts. So that tells you like the kind of your airframe health or longevity in and of itself. So that is what EICAS fundamentally is. They all look different. This is becoming more and more and more popular in the GA world, and so like you're not going to be able to escape it. Like this is something that you're going to have to look at and process. The good part is that most people now are used to like seeing this kind of information in their cars and stuff, and it's not really a weird thing at all. All right, here's a little bit more of a kind of down in the weeds look at EICAS from the 8083. It's a pretty good little diagram. Kind of gives you an idea of what one could potentially look like. So you'd have like your warning and cautions and displays on either one of these two different screens. You would so like a lot of times people will display their nav on one and their engines on the other, or you could have two pilots both looking at different things simultaneously, and they can get all their information independent of one another, which is kind of nice. You have the display switching. There's usually going to be some module that can switch back and forth. You'll have a maintenance panel that's off somewhere. That's not very common with GA, but it is very common in heavy commercial. You'll have a display select panel, so usually that display select is going to be either integrated into the switching, or it's going to be there's going to be a main panel, and the display switching are these two little bit independent ones that are just like right close to your, or even integrated into the display itself. There are redundant computers left and right, and so like you'll see the yellow lines are basically just kind of like wiring, whereas the red lines on this thing is your data bus. It means that it's a bidirectional link from the display select panel to your computer or whatnot, so that way they can exchange information and talk to each other as needed and be interrogated and respond and all that good stuff. On the bottom, it kind of shows you where all of the information comes from. So system sensors, engine sensors, it gives that raw data that goes up to the computer to be signal conditioned and then pushed over to the display. And then also all your other systems, FEC, FMC, RAD, ADC, all those kinds of airframe-like systems can also be fed into there as well as all the sensors like we had said. There's also going to be an opportunity for standby engine indicators to be tied into it as well. So in case the displays fail or there's some sort of tragedy on board that kills the cockpit information system, your standby displays are usually battery operated and totally independent of everything else. It's simply pulling data from elsewhere in the plane. Then your annunciator panel is going to be up there in the top left-hand corner where it says discrete caution and warning lights. Those are just going to be like your master caution and all that good stuff. And then aural warning is just simply an alarm that goes off inside of the cockpit based on what's going on. So it can be terrain pull up, or it could be just a stall warning or what have you. Okay, so this is what a mature EICAS system actually looks like. They generally won't call it. This is just the display page of on your 737 MAX display system. But essentially, you can see that it's going to tell you much of the same information. Not as pretty, but a lot more. I guess what's the right word? It's a lot more pragmatic and simplistic because there's just so much data that could potentially be displayed. Now, also this is for a turbine engine, so there's some things that don't apply to a recip engine, but just know that EICAS is definitely the way forward. Is the way everything's going to be in the future, and eventually you'll get to where airplanes have no standby instruments whatsoever. It's just a panel, and that's it. Now let's talk about the ECAM system, electronic centralized aircraft monitoring systems. Okay, so this is ECAM. It is the electronic centralized aircraft monitoring. Now, ECAM is a little bit different than EICAS. They both focus on the same systems. They provide the same data and everything else, but it emphasizes automation and procedural guidance. Like, so do this, don't do that. Whereas EICAS prioritizes, hey, alerting the crew, just letting you know what's going on, so that way you can make the decision. And you're going to see this start to develop whenever you start looking at both Boeing and Airbus. Boeing is going to be a lot more pilot, like in the AI world, they talk about like in the loop and being out of the loop, a human in the loop versus a human out of the loop. Okay, so ECAM is going to be a human out of the loop centric system. Now it's not. It's kind of like a misuse of the term because the human's still in the loop. They still have to do the procedure, but it's looking at it and says like the machine is correct. The human is the error prone thing. So we want to try to minimize the human as much as possible and make it as super simple for him, so that way as much as automated as possible, and he just follows the directions. That's it. ECAS on the other, or EICAS on the other, is going to say like, hey, look, the human is the authority here. We're going to give them as much information as possible, so that way they can make the best decision as possible. And this is really, really interesting because in everything else in the Airbus versus Boeing, you start to see this I guess like underpinning philosophical difference between the two. On one hand, like Boeing is going to have a lot more switches, a lot more things for you to interact with, whereas Airbus is going to be optimized for comfort and simplicity and all that good stuff. Boeing, like the A320 versus the 737, is really interesting because the 737 can still be flown. You can have a complete computer failure, electrical failure, everything fail, and at the end of the day, there's still a wire that's connected to that human or a cable rather, that the human can pull back on the yoke and pull the plane up and turn and everything that's in flight, just like a Cessna 172. Whereas with Airbus, if every possible electrical redundancy were to fail, that plane is just a rock. It's going to crash somewhere because there's nothing else that the human can do to really interact with it. Now, your Airbus guys will kind of argue because they have like all these different redundant hydraulic systems and stuff, but at the end of the day, there's nothing that has a direct tie to that human's hands to turn it and fly it. And you'll see this kind of over and over again, that like that Airbus is a little bit more, it's going to be optimized to be easy to fly and try to get the airplane to do as much as it possibly can, whereas Boeing is going to be a lot more work to fly, but the human is a lot more in charge and you have a lot more fidelity on it. Now this will lead you to what I call the Airbus reset, where you could have a 737 and an A320 side by side having the same issue. A lot of times, like with the 737, I can plug it up to ground power and I can run down just through troubleshooting what the issue is. But with the Airbus, is that like the longer that Airbus runs, the hotter it gets, the more crazy faults it'll throw and things. And next thing you know, you're just chasing gremlins in the system. And so what I always said to do, especially new avionics techs, is just that you need to do the Airbus reset. Just Control Alt Delete, turn it off, let it sit, cool down, turn it back on. Half the time the fault goes away, and that's because it's made to be super computer heavy, whereas the 737 is made to be super just kind of like bulletproof and easily troubleshot. So you'll start to see these two differences. But the takeaway here is that ECAM, EICAS are basically the same thing. Now you won't see you're more likely to see like an ECAS like abbreviation or acronym in the recip world than you will with ECAM. But either way, it all tells you the same information, does the same thing. It's just two different systems with two different underpinning philosophies. Now let's just talk about like the range markings and the instrument conditions themselves as potential places where we could have a fault. Okay, so the last thing we want to cover on engine instrumentation systems is the range and marking. So obviously we'll have different ranges that we can operate in. So if we'd say that's going to be like, in the red, we want to stay out of the red, and like this is yellow. Yellow is like you only want to be in there for a short period of time and then try to get out of it as soon as possible. And the last one is going to be the green, and so like that's where we want to keep it. Now with those range and markings, you always want to make sure that it follows whatever the flight manual says, pending or barring any like STCs that may modify a system that would require a modification legally then to the indicating system as well. This is one advantage that the digital stuff has over the analog instruments, is that the digital instruments can be modified in the settings to correspond with the reality of the engine at the time. If there's like some sort of thing that's been put onto it or whatever. That being said, that those sort of indicating modifications are fairly rare, and they're usually called out explicitly in the STC, so that way you know to do it whenever it comes out. Now, one of the things that will happen, and I've seen happen multiple times, is that you'll get a squawk that says that, like, hey, look, my engine oil pressure is low. And then whenever you go in there to look at it, the engine oil pressure is not actually low. What's happened is the gauge went out. And so it's just indicating error. And the way that you would troubleshoot that is one of two ways, depending on the environment that you're in and what you're allowed to do. You can fabricate an inline gauge and just simply hook it up into the system somewhere and then run it that way. Now, that will tell you, if you know that gauge is correct, it will let you see what the gauge inside the cockpit is doing. Now, the challenge with that is one, you have a high chance of introducing something into the system. So like if your gauge is dirty or whatever. Number two is that like you're not going to be working towards any sort of maintenance manual or any sort of task. And so it would have to be in the right circumstances for that to make logical sense. Most of the time, what they're going to do is what we call playing with the parts cannon. And so you're just going to order a new gauge, take the old gauge off, put it in there, see if you get the same reading. If you get the same reading, then you know that the gauge is probably not the problem. It's going to be something else, because if both gauges are broke, it's very, very unlikely they would break in the exact same way so that we get the exact same reading. So it's probably going to be someplace else other than that. And this could happen with any number of gauges that are out there. You just have to, the troubleshooting steps are always going to be about the same. There's other ways that you can check for gauges, and a lot of times, especially on heavy commercial world, you'll have access to the CMM. It's the component maintenance manual, and that will allow you to access another set of procedures where it'll say like, hey, look, we expect this thing is wrong. Let's try it. Another way to go about doing it is simply do a what they call like robbed parts forms, where you can take one off of one airplane and then install it on this airplane and see if that works. That comes with its own challenges. It's legal to do, and it's common practice with some certain things. The only trouble with that is that if that gauge is the problem in the system, you run a chance of introducing a problem to a whole another aircraft, and you also have two aircraft in the same setup, like side by side, that are both not being actively used. So there's challenges with every single one of those. However, it can be done. The takeaway of this like little portion is to just know that instruments fail just like engines fail. All right, so like you always have to remember that, hey, look, it could be just fine, and we have an instrumentation problem. And if you want to see an example of that, watch Apollo 13, and whenever one of the first things that Gene Grant says after Apollo 13 blows up, he's like, hey, look, is this a real problem, or is this instrumentation? And the controller's like, oh, I'll get back to you, whatever. And then later on, he's just like, they keep talking about like bangs and shimmies and stuff like that. I don't think it's instrumentation up here, meaning that like they're seeing real world effects of this indication. I don't think it's just the instrument's wrong. I think there's something actually wrong with the spacecraft in that particular scenario. Same thing happens with aircraft. It could be just your instrumentation could be off. It could be something that's really real. And so you always have to think that if you're just going off of just a squawk from the pilot, saying, hey, look, I read this in the cockpit, you want to duplicate it. If you can't duplicate it, it could be wrong. It could be a configuration issue. It could be switchology. It could be it was just a fluke for whatever reason. It could be some sort of contamination of fluid, oil, whatever. There's all these different things, but you want to be really thorough in the way that you're troubleshooting it, so that way you minimize downtime and maximize safety at all points. With that, let's talk about engine runs in the next video.